Hi everyone, let's continue our journey in set theory. So we have seen in the previous video what are sets and what are the relations that applies on set, namely the membership, the subset and the equality relation. We have also done certain questions on what it means for one to show that one set is a subset of another and when are two subsets equal. We have also shown proper subsets and what is a non-subset. We have also introduced the idea of an empty set. Now, let's take a look at certain ways of constructing new sets from old ones. These are the operations on sets. Firstly, we have the union operation. I'd just like to note that all these operations that we think intuitively, they have all can be derived from the axioms of set theory, but those axioms won't be touched on. Instead, we'll see what is the characterization property of these operations. So, A union B, what does it mean? It means that for all the sets, X will be an element of A or X will be an element of B. So, if X is an element of A union B, it means it's either in A or in B. So you can think of it as a Venn diagram. This is A, this is B. X union B is just everything, including the intersection point. What it means to be intersection? Intersection is another operation where X intersect B is, it must be in both A and B. You can just write it out in set builder notation as the following form. It's an element of A, then you choose all those, there is also an element of B. If they are disjoint, the definition, it just means that this is empty. It means that if X is an element of this and is empty, this is false, and so it's neither in A. If for all X is not in A or X is not in B. So there's no way that X can be in both A and B at the same time. So, knowing what is union and intersection, we shall move on to something that is complicated in axiomatic sense, but intuitively it's pretty straightforward. This is the complement set. The complement, there are two types. One is the relative complement. So you have two known sets in this case. If you look at the Venn diagram, you have set B and set A. They intersect at some point here. And the complement is those elements in B but not in A. Meaning, it cannot lie in this intersection, and so it only can be in B but not in A. That's what it means to be relative complement. You can also use the word difference, but I like to use the word complement. So here comes the less straightforward part. It is absolute complement. This absolute complement is dealing with the case of just writing A to AC. In this case, it is just U difference away, minus away the A. This U in this case is the universal set, or I like to better call it as the ambient set, as it's less confusing. Because in the next video, we'll show how that there is actually no sets of all sets, and that's a topic for another time. But what I like to note that in this absolute complement, usually we are aware of what is our ambient context. For example, let's take prime numbers. We know that there's no such thing as there's no prime number with decimal places. And so ambient context in this case will usually be the itself integers. But it's best to state what our ambient context is, whether it's real numbers or integers, so that when we take the absolute complement from this larger set, we understand what we are going to choose from. And if we are able to take this, we already know it's just X is an element of U, but X is not an element of A in this case. And so U needs to be a set in the beginning to be able to do this absolute complement. which just actually falls back to being a relative complement. And hence, it's good to always note what is your ambient set in context. So these are 3 operations that we can do on set. We'll see more in the next video, but let's try to understand these 3 very well first. So let's do some practice on them. Now, this is one of the laws. This is one of the De Morgan's laws actually, where A union B, the complement in this case. So I use the absolute complement while noting the fact that there is a larger ambient set in the first place, U. To this is just to reduce notation, writing too many notations. So we start with X is an element of this set, and then we use the double arrow sign. So if and only if X is the element of the bigger set, the universal set, and X is not an element of A union B. What does it mean to be not an element of A union B? It is if and only if the negation of X is an element of A union B. You can see this is the next line that it is representing. And so when you negate this, you negate the first part, you change this to an N, and then this becomes X not an element of B. So you can see how proving theories about set theory is actually very similar to proving logic laws. And so you just need to follow through the logic, which is why we have done that earlier, and see that X is no longer an element of A and X is not an element of B. And by definition, this means that X is an element of A complement because it's already an element of the bigger set, but it's not an element of A, so it's an element of B, A complement. Similarly, X is an element of B complement, and together that means X is an element of A complement intersect B complement, since it lies in both A complement and B complement. And since these are all series of if and only ifs, they are equal, because you can just repeat this whole process backwards and you see that it works. So feel free to look through again. We'll move on to the next example to better understand how we play with proving operations. So another one very common in the second De Morgan's law is A intersect B complement. We want to prove that it's A complement union B complement. You can see how similar it is to De Morgan's law, but we shall just run it through to play with more, to get familiarized with membership relation. What does it mean for A to be an element of the complement of A intersect B? As I said, the definition will be it's part of the bigger set and it's not part of this original set. Expanding out the logic, it means to negate A, X is an element of A and X is an element of B. This means that X is not an element of A or X is not an element of B. Combining this with this, you get that X is an element of A complement or X is an element of B complement. And with that, by definition, you can put them into a union, and so X is an element of A complement union B complement. And thus, you have proven this proposition. Lastly, let's deal with something a bit harder, but actually they're all dealing with logic. So if you are able to prove the logic laws in previous videos and you have practiced them, you are actually able to prove similar questions in this basic set theory course. So firstly, let's given our assumption that the intersection is a subset of C. Now we know that X is an element of A complement always C. So you can just say A minus C. You want to prove that X is no longer an element of B. So there is a direct way, but it is better to just suppose that it is an element of B, because you want things to be element of, so that you can play around the definition easier. So now there is an element of X. So you suppose that X is an element of B first. You want to arrive at a contradiction. But since there is an element of A minus C, it's an element of A and it's not an element of C. With these two in mind, it just means that X is an element of A intersect B. But since you know A intersect B is a subset of C, X element of A intersect B would imply that X is an element of C by definition. And so this leads to a contradiction. And hence, the assumption earlier that X is an element of B is wrong. And so you get that X is not an element of B. And thus proves the proposition. I hope you have understand this example. There are many examples in the books. Please feel free to try any of them. If you have any question, you can leave them in the comments down below. Please like, share, and subscribe. And I'll catch you in the other videos. Thank you.